Luciano Mari from University of Milan, who will speak on the spectrum of non-compact submanifolds and the submanifolds.
Thanks a lot, and thanks for giving me this opportunity to discuss work with a lot of Brazilian colleagues. Actually, Pacelli Bessa, Lucchesio Jorge, and Fabio Montenegro from the University of Fortaleza in Ceará, northeast of Brazil. And Barnabé Lima and Franciane Vieira from the University of Piauí, which is the state nearby Ceará, still in northeast, while Marcos Nanieri, Elaine San Paulo, and Feliciano Vittorio are from Alagoas, the eastern part of Brazil. And Elaine San Paulo, she's from Sobral, which was, by the way, one of the first places where general relativity theory was checked experimentally during an eclipse. And this is essentially collects 4 works. 2 of them were made about 10 years ago while I was in Fortaleza, and then we went back to these results and in more recent years. The purpose is to describe some effective criteria on manifolds which are non-compact to discern whether the spectrum is purely discrete or purely essential, and when some intervals belong to the spectrum. So hereafter, all manifolds will be non-compact without boundary and with dimension at least 2. I'll denote with a sec, the sectional curvature, so it's the most inclusive quantity containing information on the curvatures, on how the manifold curves. And the Ricci curvature is the average of the sectional curvature. So it's a quadratic form, and each direction gives the average of the sectional curvature of planes containing that direction. And we have a distance induced by the metric. The manifold will be called complete if it's complete as a metric space. Okay? And among complete manifolds, there's a particular class for which things are analytically simpler, are those containing a pole. A pole is simply a point where the exponential map is a diffeomorphism, equivalent to a point for which the distance function from that point is moved away from the point itself. Okay, like in Euclidean space. So the manifold is diffeomorphic to Euclidean space, so it has, let's say, trivial topology, those kind of manifolds. And our convention on the Laplacian will be that with the minus sign, so the Laplacian will be a non-negative operator on our manifold. If the manifold is complete, it's known to be essentially self-adjoint, so we take the only self-adjoint extension, otherwise we take the one in the sense of quadratic forms, okay, with its spectrum. And we split the spectrum into 2 parts. The discrete will be
you mean the Laplacian is positive?
The Laplacian is positive. The spectrum is in between 0, not non-negative. And I split the spectrum into parts in this way. Discrete is just isolated point in the spectrum, eigenvalue with finite multiplicity, and the rest is essential, which is a closed subset, okay, as usual. And I indicate with lambda of m the bottom of the spectrum. A first observation is that while a control on the discrete spectrum depends on the manifold as a whole, a control on the exponential spectrum only depends on the geometry of the manifold at infinity. If you have 2 manifolds for which you can remove a compact set from the first and a compact from the other and find an isometry between the complementary, then they have the same essential spectrum. Okay, this is called the decomposition principle. Hereafter, when I state an equality between the spectrum, is in the weakest way. That means just as sets. No claim on the spectrum measure, on the presence of eigenvalues, etc. Just an equality between subset of the real line. Okay, so let's see the first example. First example, pick a manifold which is compact with Lipschitz boundary and take its interior. Then the spectrum is discrete, Rayleigh-Kondrashov. On the other hand, pick a manifold with a constant curvature, constant non-positive curvature. So Euclidean space, hyperbolic space. I call them space forms, and the curvature will be minus k. And they are grouped by by the notation nk. So the spectrum is a half line. Please.
You say Lipschitz boundary, so you use the Dirichlet boundary condition? Or?
Yes, because in the interior, I take the extension starting from C infinity with compact support. So it becomes the Dirichlet. This half line is the entire 0 plus infinity in Euclidean space. In a hyperbolic space, it starts from this positive value. And in fact, there are no embedded eigenvalues in the sensor spectrum in these models. McKean, for the first eigenvalue, and then Donnelly observed that to have the spectrum of Euclidean or hyperbolic space, it's enough that you have a pole and that the curvature approximates, the sectional curvature approximates the constant function at any rate from below. In this case, the spectrum is the same. And same years, on the other hand, Peter Lee and Donnelly observed that as soon as the sectional curvature goes to minus infinity, any rate, and you have a pole, so you are still diffeomorphic to Euclidean space and distance function is smooth, then the spectrum is discrete, purely discrete. Okay, so discreteness does not have to do with completeness of the metric or incompleteness of the metric. And under this condition, when the sectional curvature goes to minus infinity and you are diffeomorphic to Euclidean space, the volume growth of balls in your manifold is faster than exponential. The manifold is huge. Okay, and this is not a case because Brooks, later refined by Iguchi, found a very nice general criterion. As soon as you have a complete manifold with infinite volume, if the volume growth of balls, of geodesic balls centered at a fixed origin, is not faster than exponential, then you have to have some essential spectrum. And in fact, the bound, if this bound is scaled so that equality holds in hyperbolic space, then the essential spectrum starts at most as the essential spectrum of hyperbolic space. Okay, these are classical results in the intrinsic case. What happens if you want to prove that the essential spectrum is a half line? There are two conditions. The first one is to show that the infimum of the spectrum is at least the quantity C. And this generally, geometrically, is binding, requires binding assumption in general. And then to prove that any value above the threshold lies in the essential spectrum by producing a sequence of approximating eigenfunction via Weiss criterion. And the first attempts to investigate the spectrum used the idea to produce them radial, as radial function. But this is not possible, is never possible if you don't have a pole. That's why the first result were assume that the manifold has a pole. The distance function is not a locally, no, not L2 log, sorry, Laplace of R. Laplace of R is not L2 log. Okay? And this motivated a question, which I found attributed to Yao, even though I didn't find the precise reference. What happens to a complete manifold with non-negative Ricci curvature? Euclidean space, from the point of view of comparison theory, is the biggest manifold with non-negative Ricci curvature. So somehow one may question whether, and those manifolds cannot shrink too much. So it's reasonable to suppose that the spectrum is in between 0 and infinity. And this question now is completely solved. And the complete solution, in even more than what was asked, is due first to a work of Sturm, and then to a very nice criterion due to Nelia Sheralambous and Ziki Lu in 2014, and which says that essentially the L2, once you control the L infinity norm of your candidate as an approximate eigenfunction, the Laplacian can be controlled in L1. Okay? And the key difference is that even though you cannot use the distance function, still cannot use the distance function, but you can modify it and keep track of what you lose in the L1 norm. Okay? So it's due to an observation by Japan that you can bound the Laplacian of R, the modulus, the measure, the total variation measure of this distribution. Okay. Application, through various refinements, whenever the Ricci curvature goes to 0 as a lower bound that goes to 0 at infinity, at any rate, the spectrum does not have gaps and contains the entire real line. Okay, so not only Ricci bigger or equal than 0, this is in the sense of quadratic forms. This means the first eigenvalue of the Ricci tensor is bounded below by something that goes to 0 as you diverge. And the technique and this criterion is quite versatile because it allows to prove that the spectrum is 0 plus infinity also for other structures for which the curvature is not controlled a priori. Okay, for example, those of shrinking Ricci solitons, for which the Ricci tensor is not controlled pointwise. And our research starts from the question, what happens when the Ricci curvature has a lower bound which does not go to 0? Okay. And let's see some examples. So we will study manifold with a lower bound for the Ricci curvature that depends on the radius, and that goes, let's say, to -1 at infinity. So when it's -1, typical manifold is hyperbolic space, for which I recall that the spectrum is this real line, this half real line. And under this condition, we know that the essential spectrum starts at most at this threshold, okay, by Brooks' criterion. Two classes of examples which are topologically non-trivial are those of conformally compact asymptotically hyperbolic manifold, which are manifolds which converge to hyperbolic space very quickly at infinity. And this class of manifold, Mazzeo proved that the essential spectrum is the same as that of the hyperbolic space, and interestingly, with no embedded eigenvalues. And in some cases, you can even say that the full spectrum is the same of the hyperbolic, that of the hyperbolic space, which is the case by a beautiful theorem by John Lee, and later he proved that Shodong Wang, who considered Poincaré Einstein manifold, for which the Ricci curvature is proportional to the metric by the constant as the one in a hyperbolic space, and for which the boundary at infinity has a admits symmetric with non-negative scalar. And these assumptions, non-negative Yamabe invariant, I wrote this way. So under this assumption, the full spectrum is characterized, and there are no embedded eigenvalues. And the other class is that of hyperbolic manifolds. Okay, and with reasonable group. In this case, the essential spectrum has no gaps as well. And by a criterion of Sullivan, if once you have an hyperbolic group, you have the notion of limit sets. So you take an orbit and see the closure of the orbit, how big is the intersection with the boundary of hyperbolic space. You measure the Hausdorff measure of this intersection. If it's not too big, that means the group is not too big. Okay, that means the quotient is big. Then the spectrum, the full spectrum, is the same as that of the hyperbolic space. Otherwise, the first eigenvalue gets smaller, so you have some discrete spectrum before. And indeed, in this case, you don't have embedded eigenvalues. Okay, so in these two cases, let's say reasonably amenable manifolds, infinity somehow, you don't produce gaps in the essential spectrum. But, so the question is, can you produce gaps? Yes. Yes, and even a lot. There's a paper by John Lott. John Lott constructed for every epsilon, a manifold with finite volume. So at infinity, looks like this with some perturbation, like a cusp with some perturbation. With finite volume, sectional curvature epsilon close to -1, so close to be hyperbolic, and whose essential spectrum has infinitely many gaps. And some of the ideas of the construction are based on construction of Schrödinger operators on manifold with infinitely many gaps. So these, some of these constructions were more or less inspired by results in Euclidean space for operators with a potential. And what about manifold with infinite volume? Well, you can, when you have a lower bound for Ricci, which is non-zero, you can somehow play with periodicity. And Shane and Tran, in 2016, proved the following. Take any nice manifold, like Euclidean space, bounded curvature, positive injectivity radius, like Euclidean space, fix a maximal collection of balls, and then conformally deform the metric in this ball in such a way that each of these balls looks like almost a sphere. So this manifold looks like a bunch of spheres. Each has discrete spectrum, and by carefully controlling the necks and the parameters, you can produce a manifold which has any fixed, at least any fixed number of gaps, but finitely many. It's not known whether one can produce infinitely many gaps with infinite volume. And a second question is what's the relation between the gaps and the curvature lower bound on the manifold? And this construction does not give clear indication on how negative should be the curvature to produce gap in a fixed region. Okay, so this motivates some. Please.
Oh, is it clear why it's easier in the previous theorem of Lott to have infinitely many gaps, and in this case it's just
Because periodicity here is the proof are, I should say, I don't know very well the proof of Lott. It's quite complicated, this paper. This is, I should say, I know this better and it's simpler. Idea. I think that periodicity does not match well with finite volume. If you want something periodic, you produce. But I think it doesn't use kind of periodicity. I mean, okay. I should check. Okay. So these are somehow natural questions. Suppose that the Ricci is bounded below, but you have infinite volume, so you avoid Lott. Question 1, can you prove that the full spectrum of a hyperbolic space is contained in the spectral spectrum? This is quite, I say, unlikely. These two questions, perhaps they have a negative answer. One may also ask if there exists at least some interval at infinity. So you cannot have gaps at infinity. But it's just a question I don't have. I would more incline to say this none of them hold. But this is more reasonable, I think. If you have a positive first eigenvalue, so when a manifold has a positive first eigenvalue, it has exponential volume growth, so it's far from being compact. And the question is whether there exists a threshold after which you'd only have essential spectrum. So once you have positive first eigenvalue, it's difficult to produce, it's impossible to produce gaps converging at infinity. An example of manifold with a positive eigenvalue, it's like pick a flat manifold and pick a tube, exponential tube. So you have a cusp here and a funnel here, okay? And this is the typical manifold with a non-typical. It's an example of manifold with no negative first eigenvalue. And our, please, sure.
If you know that you don't have gaps to infinity, do you know whether or not you have infinitely many gaps before?
Sorry, if you know.
If you know you have no gaps to infinity, does that leave open the possibility that you could have infinitely many gaps before the gaps finally finish?
I know of no example nor counterexample. It might happen. Might happen. Yes. Our first result is an answer to this question in the maximal case. Okay. Look at when I have a manifold. To state it in its more general form, I just recall what an end is. An end of a manifold with respect to a compact set. Pick a compact set and pick this is an AND. That means it's a connected component of the complement with non-compact closure. This is not an AND. Okay? So this is a big AND, and this is a small AND. Okay? And the theorem is the following. It will prove, pick a complete manifold with a Ricci curvature bounded below by something that converges to 1. And it converges fastly to 1. So faster than 1 over t, okay, at infinity. If you have an AND with infinite volume, so like this AND here. If you have an AND with infinite volume and maximal first eigenvalue, compatible with the curvature bound, then the whole spectrum of the hyperbolic space is inside. So from this value on, you cannot produce gaps. And in particular, if the AND is the entire manifold, say if the entire manifold has maximal first eigenvalue, then you have the spectrum of the hyperbolic space. Okay. Okay, this is the, so what, let me just write down a more, okay, so I will this way, no, let me write down a simplified statement. Okay, and for the sake, where can I erase? Ah, okay, thanks. Okay. A simplified statement is the following. Say theorem 1. Ricci bigger or equal than -1, first eigenvalue maximal, then spectrum coincide with that of hyperbolic space. Okay. Yeah, the big AND is, let's say, M itself. Okay. This is more general. And an interesting question is whether you can find embedded eigenvalues in this case. Why it's interesting? Because there is a recent work by Svetlana Itomirskaya and Liu, who produced on radial examples satisfying this condition, but not this condition barely. They produced even you can even produce a countable number of embedded eigenvalue, even in a dense subset. Okay? Barely means that they can allow for Tf of t, let's say, to be bounded above by some function eta of t going to infinity at any rate. So a little bit worse than 1 over t, you can produce countably many. If you want to produce finitely many, you can even put a constant here. So it's really borderline. And in radial example, if this goes to 0, then you have no embedded eigenvalues. So it's, but the problem is that to control eigenvalues in a manifold is very binding. It's very difficult. Requires in general binding condition is done via relic identities, and these actually require more structure on the manifold. So I should say we are far from answering, with the techniques to prove this theorem, we are far from answering this question. And probably we need more control, like an exponential approaching. No. Okay, this is the criterion concerning the intrinsic case. No, please.
So if you have infinitely many gaps, then what you can say geometrically about the ends? There is any such thing that
Not that I know. There is a paper by Peter Lee and Japan Wang. It's a classical paper 2002. They have a couple of ones who study the geometry of manifold with this Ricci curvature lower bound with 1 and positive first eigenvalue. And in this case, either an end grows, let's say, like a funnel exponentially, or an end has finite volume and shrinks exponentially.
there is no topology in the end? Because, I mean,
Well, the end can have even infinite topology. So as assertion like you have finite topology, with a Ricci curvature, with a lower bound, you can produce infinite topology. You are not, this curvature condition is not enough to say that you are diffeomorphic to the interior of a compact manifold, okay? What about the extrinsic case? So we will consider isometric immersion in Euclidean or hyperbolic space, and we will consider minimal ones, okay? That means we have a second fundamental form. If you think about hypersurfaces, second fundamental form measures the variation of the normal vector, and it's a quadratic form. Its trace is called mean curvature, and the manifold is minimal if the mean curvature is 0. Variationally, they arise as stationary points for the area functional of the hypersurface with respect to compactly supported variation. And the question is when the spectrum is that of, so among these submanifolds, you have trivially the totally geodesic ones, hyperplanes, subspaces, so which have the same curvature. In this case, the manifold is a space of the same curvature and the dimension of the submanifold. So the spectrum is the same. This is triviality. So these are the most well-behaved, the totally geodesic ones. And on the other hand, if you pick a, say, minimal submanifold with boundary, you remove the boundary, the spectrum is discrete. So these are more or less the antithetic cases. Okay? And we will produce a criterion to guarantee that the spectrum is close to that of a totally geodesic space, and one to guarantee that the spectrum is discrete. Okay?
Sorry, what is MK?
Is that this is Euclidean or hyperbolic space of dimension n. This is the Euclidean or hyperbolic space of the same dimension as your submanifold. Okay? So you essentially, if you have your submanifold, you compare your submanifold with the totally geodesic. Your M, and here is your NMK. Okay, you compare with the totally geodesic. Okay, so to understand which kind of conditions is useful to require to get information, we need to study the examples that were produced. Okay, and we start with the solution of Plateau's problem. So given any Jordan curve, this was done by Radeau and Douglas in 1930, given any Jordan curve, that means embedding continuous, so even unrectifiable, whatever, there always exists a disk with minimizing area, so in particular it's minimal, among all disks with boundary gamma. Gamma can have portions where it's not rectifiable. And another class of important examples have been given as counterexample to some conjectures, problems proposed by Calabi in the 60s. And Calabi proposed in the 60s that to prove or disprove the following claims: a complete minimal surface in Euclidean space cannot lie in a slab unless it's a plane, cannot lie between two parallel planes unless it's a plane, and even more, it's not bounded. Any complete minimal surface is not bounded. Both conjectures turned out to be false. In 1980, Georges and Xavier, in a paper on Annals, they constructed a complete minimal hypersurface in a slab of R3. And in 1996, Nadirishvili, highly refining these ideas, introducing other tools, was able to found, it's a paper in 96, in Invenzione, to found the first example of bounded complete minimal surface. This construction motivated a full literature, and Yaus asked about the spectrum of this example. Are they spectrum discrete or not? In general, for this construction, the spectrum can even be the full 0 plus infinity. So you have no control on the curvature. Please.
Is it immersed or
Immersed? Immersed because if it were embedded, this is a plane. This is a plane. If it were embedded, an embedded plane by a theorem by Kodimini-Kotze should be proper. Okay. This doesn't exclude indeed. Well, if it's proper in a slab, it's a plane Hoffman mix. So it's an immersion, and it's an immersion this as well. This construction motivated a full literature in the past 20 years, and where they found construction more and more sophisticated with control on two things. With control on the limit set of the immersion. What is the limit set of the immersion? Is the set of points in the ambient space, which are limit points of images of sequences that diverge in the manifold. Okay? So here we have a manifold, a sequence that divergent tends to a part of the limit set in the boundary of our set and part of the limit set in the interior. Okay? If the limit set is only on the boundary, we say that the immersion is proper in omega. That means the preimage of compact set in omega is compact. You don't have this behavior. You just tend to the if you tend at infinity intrinsically on your manifold, you tend to the boundary in the image. And they were able to produce examples, complete, minimal, with the limit set even fulfilling the entire boundary, but contained in the boundary. Okay? So this minimal is complete, but it's proper in, let's say, the ball in omega. And the second example, which was really surprising, is related to Plateau's problem. They produced the following. This is Martin Nazirashvili, and then extended with Alarcon by Alarcon. Pick any Jordan curve in R3 and any epsilon. There exists a complete minimal disk whose such that the immersion extends continuously at the boundary. The boundary is non-rectifiable, but it has Hausdorff measure 1. It's a Jordan curve, and it's epsilon close to your given Jordan curve. So you have plenty of complete examples, essentially. And starting from this construction, you can produce example with dense. You can produce density theorems for those complete minimal surfaces, and so forth. There's a
construct the limits exactly. Can you repeat that? I'm just curious. I've seen this before.
This one, the second one. The statement is the following: if you fix any Jordan curve, an epsilon, that means an epsilon neighborhood, there exists a complete minimal disk with a continuous extension on the boundary, and the image of the boundary is a Jordan curve, so the image is injective and is an embedding, and this Jordan curve has measure 1, has dimension 1, out of dimension 1, but it's not rectifiable, and is epsilon close to your original curve.
It's a symmetric map, or like some regularity.
Sorry.
Is it some kind of quasi-symmetric map between those?
No, it's I mean the construction is the construction is produced by using complex analysis and deforming with an iterative procedure, deforming Weierstrass data on the manifold. Let me Just if you have a disk, the idea is that you construct a sort of bricks, this regions like this, around the boundary. You deform the Weierstrass data to have a big metric here. So if a curve in such a way, essentially, so you intrinsically deform it in such a way that if you have a curve that diverges, yes, it has to pass a lot of these regions, and so it must have infinite length. But extrinsically, each step goes orthogonally from the one above, and if you increase at each step by 1/n, the series diverges intrinsically, but here, if you increase at each step by 1/n on orthogonal direction, you increase the distance from the origin by 1/n square. So it keeps bounded. And these constructions start with a similar technique, starting from the boundaries. They're very, very nice. There's a beautiful paper by Collan and Rosenberg with a detailed proof of Nadirashvili's paper. Okay, so we have this example, this condition, and our criterion applies to those examples. If you take a minimal surface, any codimension, in a bounded convex set, pick the limit set inside of omega. You don't care about the part outside. If this limit set is out of dimension less than 2, then the spectrum is discrete. So the point is that the limit set cannot contain, let's say, disks, copy of two-dimensional things. Okay, so it doesn't require the completeness of our surface, so it applies to, for example, to solutions of Plato's problem. And it's not actually something that is really bound to minimal surfaces. As a corollary, for example, if you take any Jordan curve with outer dimension less than 2 and containing a certain diameter, then any surface spanning gamma with constant curvature less than 1/r must have discrete spectrum. Okay, and gamma could be a, let's say, type of Peano curve, so it can be even, it's not really one dimension. This condition can be improved a bit. Actually, what is enough that the Hausdorff measure of, let's say, the limit set is 0, where psi of t is t squared log t. So a little bit less than t squared. Okay? When this measure, so it's very, very close to h2 equal to 0, which is this chart. We fail by a logarithm. Okay, this is the first criterion. And the second criterion, what happens in a higher dimension? In higher dimension, our proof fails. So if you put here m, you would expect m here. So the conjecture is this one. But we are not able to raise the dimension. We can treat higher dimension, but here we still have 2. And it's a problem of the proof. Our proof is non-optimal. Okay, what happens when the spectrum, so how to prove that the spectrum, which conditions are reasonable to assert that the spectrum is that of a totally geodesic slice? There is a binding condition for which everything is known. That means if the manifold has second fundamental form integrable, it's well known that at infinity resemble planes in Euclidean space, so the spectrum is 0 plus infinity, and the same in hyperbolic space. So it's quite very tame at infinity. This is the image of the catenoids, that's a typical example. But there are other examples which do not have finite total curvature and were constructed by Michael Anderson in 1982, who solved the Plato's problem at infinity in hyperbolic space. So if you pick the Poincaré ball model in hyperbolic space, pick a submanifold, like a Lipschitz submanifold or even smooth, there always exists a minimal, a proper minimal immersion, we will deal with proper ones. That means no limit set. You go at infinity, you don't accumulate anywhere in the ambient space. And Anderson constructed proper examples, so plenty of proper minimal hypersurfaces by variational methods, solving Plateau's problem. Okay, and this is the kind of example we want to treat. So what's the spectrum depending on the boundary regularity of the boundary. And the function that we want to control is the density function. The density function goes this way. Pick a point in the ambient space. Let's say a point also in the image of the manifold. Pick a ball of radius r and measure the quotient between the area inside the ball and the area of the totally geodesic slice. The area inside the ball and the area of the totally geodesic slice, I call it Vk. V0 is r to the m, Euclidean space, Euclidean ball. And this V1 is hyperbolic sine, the integral of hyperbolic sine, so it's e to the m-1 r. Okay, this function is monotone increasing. That accounts for the fact that a minimal submanifold is messier and messier as you go farther in space, as you look larger and larger. And we say that the manifold has finite density if and only if the limit is finite. Okay? And the reason why we look at this condition is because Anderson solutions are constructed to satisfy this condition. And this is the natural condition that one uses to construct example by geometric measure theory. Is the quantity one wants to bound is the mass to produce something in the limit. So it's natural. And this is our second criterion. If you are a proper minimal immersion into a space form, if you are in hyperbolic space and your density does not grow faster, it grows slower than exponential, or if you are in Euclidean space and your density grows lower than polynomially, then the spectrum is the entire coincides with that of the model. Okay? So in particular, it applies to Anderson solution, irregardless the boundary regularity. So as soon as the boundary is decent for Anderson, it's just an homological, it's a current with a homological property, then the spectrum is always, they have no gaps. And one interesting point here is that there's a very nice result in 2022 by Bessa, Gimeno, and Polymerakis that says that, so our theorem in Euclidean space requires that the density grows slower than any polynomial. So it's not much worse than being finite. Okay? They prove that if the density does not grow faster than grows slower than a quadratic exponential, then the infimum of the spectrum is 0. This is quite surprising because manifold with a quadratic exponential can have discrete spectrum. Those examples by Lee and Donnelly, as soon as you go over exponential growth, you can produce finite example. But if it's minimal, the bottom of the spectrum is 0 under very much weaker condition than those guaranteeing in our theorem. And this is quite straight, but they don't claim that the spectrum is 0 plus infinity. And in fact, our theorem is quite rigid. The estimates are really something that fix exactly, so it's not much space to work to improve these conditions. Okay, now I think I have it's 44, so what, 10 minutes? 10 minutes? I would just, I wanted to, this is the proof of the criterion for the discrete spectrum. I want to say a couple of words on this last criterion, also because this is the most recent work. But just a couple of words. of words. So this is the intrinsic case, the extrinsic case, say theorem 3. Let's say in hyperbolic space, proper minimal. Let's say the spectrum is that of hyperbolic space if the density does not grow too fast at infinity. Okay, these two theorems are proved by a common technique, and the approach is not that has nothing particularly strange or surprising. What do? The comparison model is hyperbolic space. So you pick, let's say this is the volume of spheres in hyperbolic space. What you pick is the radial function in hyperbolic space. That is the approximate eigenfunction. So for every value, we want to construct the approximate eigenfunction. For every value above the threshold, you produce an oscillating solution, and which is approximately the eigenfunction. You cut it off with a eta, which is kind of this, from T to S. And you choose as your candidate to be characteristic approximate eigenfunction, a function of some b that should mimic the distance function to a point. So the point comes, switches to which kind of function b is effective to use. We cannot use the distance. We cannot approximate it because with this lower bound of the curvature, the previous approximate convolution procedure produces errors which are difficult to handle. You have to be more precise. So which choices? Here, the choice is obliged. So is very natural. You choose the distance in the ambient space. Okay, so you have your hypersurface, you fix an origin, and you pick the restriction of the distance to this hypersurface. Here, not. Here, the choice we do is a reparametrization of the green kernel of the Laplacian on the manifold. Under this condition, it's known that you have a minimal positive green kernel, kind of this, with pole at a given origin. Okay, in Euclidean space, the green kernel is r to the 2 minus m. Okay, it's a radial function. And you define a function, a fake distance as follows. You have, this is the kernel of your model, and you have the kernel of hyperbolic space. The kernel of hyperbolic space is a function of the distance to a point, and it's exactly this function. It's explicit. It's a radial function, it's explicit. Okay? It's the integral of 1 over the measure of the spheres. This is the kernel of the hyperbolic space. Define B in such a way that green kernel is that of the hyperbolic space evaluated in B. So if you are on hyperbolic space, B is the distance to a point. If not, B is something that resembles the distance. Okay? And here you have the extrinsic distance. So the gradient is no more than 1. Key property. And here, key property, the gradient of the fake distance is no more than 1. In Euclidean space, these fake distances were used by Koldin and Minikotz in a series of papers. And we're able actually to construct and prove this property also when the model comparison is not Euclidean space. And this proof is not easy, but it's crucial. So our function has gradient no more than 1. But it's not proper. This function is not proper. Look at, this is proper, this goes to plus infinity. If I not leave, green goes to 0 at infinity, which is not guaranteed. In our manifold, under this condition, green may not go to 0. So our functions are not proper. So these are not compactly supported, but you can handle with some potential theory. Okay? And you want to produce for varying T and S function for which this quotient is arbitrarily small. Okay? On the one hand, the L2 norm of your test function is bounded below by what happens in the smaller interval that involves a flux of your function B. And on the other hand, the upper bound involves how far is the gradient from 1. So what you want is to bind the distance between 1 and the gradient in an integral sense. And just a final slide. So the quantity to look at is the flux. And the flux is related to the density, because the density is measured the area of the region where B is less than sigma divided by the corresponding one in hyperbolic space. And you see that if B is the gradient of B is no more than 1, this is bounded below by something which is an integral of the flux. So the density bounds below the flux. And the key to get this theorem is that the flux bounds from below the density is bigger than the flux, and here the flux is bigger than the density, and the flux is monotone as well. Like monotonicity for the density is classical, monotonicity for the flux a bit less. But this double control is the key to get the theorem. And in theorem 1, things are a little bit different, because since it's a reparameterization of the green kernel, the flux is identically 1, and the density is bigger than the flux, but you don't have the reverse inequality. So you have to have a bound on the density in some other way. And the first eigenvalue, the rigidity given by the maximum first eigenvalue gives you that bound, gives you that this term is more. So the idea of the proof is very same, is the same, but the kind of problems are kind of somehow dual to one another, somehow. Okay.
Is this sharp, this theorem, that you can construct examples to fail without the condition?
No, we don't know. The proof of this theorem and this is very sharp. You don't have much to move. Just to give you, for example, this condition. Long way. Okay. For example, this condition, if you move away from this condition tells you that we are not comparing to the hyperbolic space, but to the model associated with this. And this condition says that this model has the same order of growth, volume growth of the hyperbolic space. If you move from this condition, even comparing with this model and hyperbolic space is much more complicated. But if you lower this eigenvalue, you create exponential errors in our technique, while you have a polynomial controls on the various quantities. So it's by far, one had to work to introduce new tools. Okay, so I think thanks a lot for your attention.
Just You're using the minimality of the surface in the, or the minimality of the manifold, submanifold in the analysis of the density function. Is that what is important?
It appears in various steps. The fact that the density is monotone is crucial. For example, sorry, but this, I don't want to use more time, but there's a, if you don't have minimality but just a constant mean curvature, in this theorem we don't know. And you have the reason. There is one reason. I just was just one slide. Yeah, this was my last slide, and thanks. And this was one slide of questions, and one of them is what happens when bounded density and constant mean curvature is the one. And the reason is this computation that governs that appears in all of the three theorems. If you have a function in the ambient space and you compose with the immersion, the Laplace of u is the trace over the tangent space of the submanifold of the ambient Hessian plus the mean curvature vector against the gradient of the function. So if the mean curvature is 0, you only have the, if it's not 0, you have to control the angle. And it's very difficult to control the angle using an integral estimate. Okay, so, and this is the very equation governing also the theorem for the criterion for the discreteness of the spectrum, which also apply when the mean curvature is not too big. And in fact, is not something that the estimate of the spectrum, since the function constructed of this sort, comes from an estimate for the principal eigenvalue of a fully nonlinear operator in the ambient space. So it can be recasted. The third work we did is recasting this first criterion for the discreteness of the spectrum as a Faber-Krahn inequality for a fully nonlinear operator. Is the and the extension of this Faber-Krahn to higher dimension is an open problem.
Thank you. So, are there any other questions? If not, let's thank the speaker again.